Hello, I'm Jonathan Lorraine. I'm presenting our paper, Lyapunov Exponents for Diversity in Differentiable Games, with my collaborators Paul Vickel, Jack Parker Holder, Tal Kochman, Luke Metz, and Jacob Forster. Now, to quickly overview our paper. When solving optimization problems, randomly initializing and then optimizing can fail to find different solutions. For example, agents in the iterated prisoner's dilemma will often learn to battle instead of cooperating, leading to lower welfare for everyone. Here, we present a way to generalize Ridge Rider to optimization in differentiable games by providing a method that finds bifurcations and then branches the optimization process across them. Notably, we find bifurcations with Lyapunov exponent-based objectives. So, why might we want to find different solutions? In image classification, solutions using shape information might generalize better than those using texture information. Or, in differentiable games, our agents might receive higher rewards by finding solutions where they cooperate instead of simply battling. But, what exactly is a differentiable game? Differentiable games generalize single objective optimization. Each agent has a separate set of parameters and a loss that they optimize. Differentiable games are increasingly important in machine learning. Examples include GANs, hyperparameter optimization, meta-learning, self-play, learning models for RL, adversarial examples, and many others. Today, we'll focus on the iterated prisoner's dilemma, and later also we'll look at scaling up to GANs. The iterated prisoner's dilemma is an infinitely repeated version of the prisoner's dilemma where agents choose to cooperate or defect in each round. Here we have two notable solution modes. There are defect-defect solutions where agents always defect or battle with each other. There are also tit-for-tat solutions where agents repeats what the opponent did in the prior round. Tit-for-tat facilitates cooperation among the agents, allowing for higher welfare. Ridge Rider is a method for finding diverse solutions in single objective optimization. It does this by branching optimization at saddle points. Optimization is branched by following or riding the most negative eigenvectors of the Hessian in descent directions. They apply this for improvements in varied applications like zero-set learning and out-of-distribution generalization. But what if we want to use Ridge Rider to find multiple solutions in differentiable games with multiple agents like the iterated prisoner's dilemma, which we shorten to the IPD? There's no single loss for differentiable games, so there's no single Hessian with eigenvectors to follow. Here, Ridge Rider isn't even defined. Now, a quick definition. Bifurcations occur in a trajectory when a small parameter change causes a qualitative difference in the trajectory. For example, bifurcations in optimization can lead to different final solutions. Now we can see a key insight. Ridge Rider found saddle point bifurcations and branched across them. In single objective optimization, the only relevant bifurcations of saddles due to conservative dynamics, but there are many more bifurcation types for non-conservative dynamics in differentiable games. Maybe we can generalize Ridge Rider's method to differentiable games by looking at finding more general bifurcations than branching across them. Now, let's look at some toy problems to illustrate different types of bifurcations. Here, we show an optimization problem with a saddle bifurcation in the center. When we perturb the parameters of the bifurcation, the optimization separates into different solutions, one in the top right and one in the bottom left. In each color, we show a different perturbed trajectory or optimization branch. Next, we show a hop bifurcation, where the system stability switches and a periodic solution arises. This is a new kind of bifurcation that occurs in differentiable games and not single objective minimization. Sometimes, the periodic solution has an exceedingly small basin of attraction, making it difficult to find with random initializations. Now, let's look at a framework for finding multiple solutions. To do this, we propose a branching optimization tree search. The key parts are selecting a starting point, creating different branches, and choosing when to rebranch. This animation shows the steps to the branching optimization tree search. But we still need a way to find bifurcations to branch optimization. Let's briefly introduce notation to explain a method to find them based on Lyapunov exponents. Remember, each agent has its own objective in the differentiable games optimization problem. For simplicity, we create notation for the concatenation of the players' parameters and gradients. This allows us to write the optimization method as a fixed point operator concisely. We can write out the fixed point operator for various optimization methods, for example, with gradient descent, where both players update their parameters simultaneously. The Jacobian of the fixed point operator is helpful for analysis of parameter trajectories. For example, the convergence rate near fixed points is bounded by its spectral radius. We are interested in finding bifurcations where trajectories rapidly separate towards different solutions. This equation roughly measures how trajectories will spread out at some point omega in some direction d, using the Jacobian of our fixed point operator. Wielding this intuition, let's look at what Lyapunov exponents are. Here, we show optimization trajectory iterates from an initialization omega 0, in black, accumulating at a fixed point omega star. Also, we show two different perturbations, d1 and d2, along with their perturbed trajectories in blue and green. The Lyapunov exponent for an initialization and perturbation roughly averages the log of the spread along the trajectory. Most theory deals with arbitrarily long optimization horizons, but we focus on truncated ones. Also, we primarily focus on the direction maximizing the exponent, so-called maximal Lyapunov exponent. Here, we show a heat map of the max 10-step Lyapunov exponent. We also visualize the calculation of the exponent in those regions. First, we show optimization trajectories near the center, where they don't separate. Note how the Lyapunov exponent is small. Next, we show trajectories near a bifurcation, where the exponent is maximized. Here, we show optimization trajectories for gradient descent on the max 10-step Lyapunov exponent. For various initializations, we can find bifurcations, showing we can use gradient-based optimizers to find a starting point for our branching search. But we've only looked at 2 bifurcation types so far. Can we construct toy problems with more varied bifurcations to test our method? We use a simple idea to construct many more 2D problems. Simply take your favorite differentiable game and have each player optimize in a random subspace. We must make a few choices for reasonable optimization dynamics in the subspace. Check the paper for more details. Here, we show the random subspace toy. First, for the iterated prisoner's dilemma, where the full-scale problem has 10 parameters. Then, for the mixture of Gaussian's GAN, with about 500 parameters. The exponent peaks near where the trajectories separate, showing we can also find bifurcations here. This is also the GAN. Here are the prior plots for various other random seeds, and we can see a diversity of bifurcations. It would be interesting to see if we can get any insights into the full problem from these random subspace toys in future work. Now, let's try the full branching optimization tree search, called Generalized Ridge Rider, or GRR, on the iterated prisoner's dilemma. To summarize the key points to our method which we investigate. First, find a suitable starting point for our optimization process by maximizing the exponent. Then, select branching directions or perturbations from a given branch point using the associated maximal direction from our exponent calculation. Next, continue the optimization process along a branch after the initial perturbation. Now, let's look at these components on the iterated prisoner's dilemma. First, we look at randomly initializing, then applying an optimization method. Each existing baseline method only finds a single solution mode even after 20 random initializations. Next, we look at our method, which finds both solution modes. Also, we look at doing our branching optimization without tuning the exponent. Here, branching doesn't affect the solution, which shows that it's important to tune the exponent if we want our perturbations to cause bifurcations to different solutions. Next, we use our method to train ensembles of a mixture of Gaussian GANs by branching optimization. It's difficult to differentiate through the exponent for gradient-based optimization, but we can evaluate it. We see evidence that our method may be able to find ensembles of GANs that cover more modes, helping to prevent the mode dropping problem. But the main takeaway is that our exponent calculation is scalable to realistic full-scale problems with deep neural networks. We also include results in our paper applying our method to a full-scale single-objective optimization problem from Ridge Rider, showing improvements. With that, I'd like to thank you for watching. Feel free to send me an email with any questions or if you'd like to chat about the project.